Hi guys, welcome to a special Learn Electronics Repair video. In this video we're going to look at a very common problem we find with graphics cards and motherboards in particular. And this problem is called a short circuit high side MOSFET. I'm going to show you in this video at least 10 ways to trace this sort of fault as to which MOSFET is a short circuit one. Some of these methods are quite novel and probably have not been shown before anywhere that I've ever seen for sure. So whether you're a beginner, whether you're intermediate, or whether you're experienced with GPU repair, I think you're going to learn something in this video. In fact, I'm sure you're going to learn something in this video that you didn't know. I'll divide the video into chapters so that you can skip through to the various different techniques I'm going to use. And also, if you want to refer back to this video later, if you want to use one of these techniques, it'll be easy for you to find that information that you want to watch again. So if you like, you can skip forward now to the various chapters in this video. But I'd like to think you'd want to watch the whole thing. And if you do watch the whole thing, I'm sure you're going to learn a lot. So to start with, this is a graphics card that has a short circuit high side MOSFET. I originally started to make a video with this. It belongs to a subscriber, and he thought it may have been put into a mining adapter the wrong way around. If you connect a mining adapter the wrong way, you're going to damage the GPU. And I was making a video with this card. I started to make the video and then realized this was an ideal opportunity to create this tutorial. So first, let's have a look at the graphics card. It's an RTX 2060. Let's have a look to see what is wrong with this graphics card, although I've already told you. And then let's have a look to see the various ways in which we can actually trace the short circuit component. I have 5 graphics cards here which were brought in by 2 subscribers, Lewis and Alvaro, who live on Gran Canaria, where I live and work. They're in the capital, Las Palmas, and they use these for currency mining. They contacted me and asked me if I would look at these, so I said I would, and I made my usual offer, which is to everybody. I offer a no fix, no fee service. If I can't fix it, it costs you nothing. I offer fixed price repair, so if by the time I've diagnosed a problem I've basically fixed it, then it's €45. If I diagnose a problem that requires parts, or it's going to be quite a big job, BGA rework and this sort of thing, then I'll negotiate a price. And if you don't like the quotation, back to the original. I can't fix it, you owe me nothing. So that's how I work. And Lewis and Albert liked this, so they brought me these 5 cards. This is the first of them. It says obviously Zotac GeForce GTX 1060, but it's not actually containing what it says on the box. So we have the backing plate, which is being removed, and we have the graphics card in the anti-static bag, yes. And this is the card. So it is a Zotac, but it's a GeForce RTX. And it's an actual fact, if I can find the model number of this for you, this is an RTX 2060 6GB graphics card. So there's the card, and the information I have with this one is that they think it's been inserted into a mining adapter the wrong way round. If that's the case, it's probably not repairable, but it's very easy to work out if that's happened to a graphics card with a simple check before we check anything else. So because we have an idea what the problem is with this, let's go straight for it and see if we can prove that very, very quickly. This is a mining adapter, and it runs in PCIe single channel 1x mode, and this is the little adapter that fits into the PCIe slot on the motherboard. And it's very easy to insert these things the wrong way round. And the problem is, if you do, that some of the signals here, which is the first PCIe lane and the reference clock, end up connected to the 3.3 volt supply, and that destroys the GPU normally. So let's see straight away if that's happened, and the way to find out is just to check on the PCIe fingers. We have the multimeter in diode test mode, so I'm going to test from ground with the black lead to the PCIe. On this side, I'm interested in the third and fourth finger after the notch. So 1, 2, 3 is reading 4, but as it settle down, 5.6, 5.7. Normally they don't climb up like that. And the fourth one, interestingly the same. Normally they just steady. I'll just check, make sure my meter leads are connecting properly once more. So 4. That in itself is a little bit unusual, but I haven't looked at these 2000 series cards before, so I can't say for certain. That's what I have, and we need to check, are they both shorted to each other? And the answer is no, they're not shorted to each other. So there's no shorts to ground or open circuits there, but I find the increasing resistance slightly strange. Maybe you guys have seen that before, all the time it's completely normal. On this side of the board, I'm interested in 2 signals. So the first one is on pins 2 and 3. And this is ref clock plus and minus, or reference clock. This is a 100 megahertz clock that synchronizes the transmission of data between the GPU and the PC. So we'll have a look at these. I'll just check the meter. Yeah, it's good. I'll go to ground of the black lead, and let's have a look to see what's on pins 2 and 3. So here's pin 2, and that's reading 800 steady, and pin 3, 800 steady. Again, I can't say exactly what they should read, but they should read the same as each other, and they shouldn't be shorted to each other, which they're not. So that's those 2. And then the other signal, you can probably see the trace here. Just going here, again, 2 pins, pins 5 and 6. And this is the first PCIe lane, if you like. This is half of the lane, the other half is on the other side of the board, on pins 3 and 4. So there's 4 pins make up one lane. So on this, again, we need to have a look. So you've got 1, 2, 3, 4, 5. Now that reads open circuit, and pin 6 reads open circuit. And this is actually okay, and the reason it's okay is because these tracks go to all these capacitors, so I need to test from the other side of the capacitor. Well, because of the capacitor isolating these pins from any voltage on here, there shouldn't actually be a problem on these ones. So we'll have a quick loop. So we can just go, I'll show you, from pins 1, 2, 3, 4, pin 5, we'll go to the capacitor. Here, yeah, and pin 6 will go to the capacitor afterwards. Okay, and then from the other side of the capacitor to ground we have. That's how I'd expect it to read, with a bleep, yeah, and steady. Yeah, that's how I'd expect it to read. They're okay. Let's have a quick look on the other side again. So this is the side without capacitors that's more prone to damage. So pin 3, strangely enough, it does bleep now, it didn't before, but then it's climbing up, and I find that a little bit odd, yeah. Pin 4. Let's have a look at the next lane. So if you look along here, I'm sure you can see where the lanes are. So 3 and 4 have little tracks going from, and if I'll use the microscope, it's more clear. There, that's a little bit clearer, especially if I use the torch. So you can see pins 3 and 4 have the 2 traces coming to them, the ones that we were just looking at here, okay? And then you can see the next lane is here, these 2. So again, let's have a look at this one, and let's just see how it's reading. This would not directly have connected via the mining adapter. It wouldn't be going anywhere, no matter which way around you had the mining adapter. What's on these 2? Well, I'll just get a good ground. Okay. And that's doing the same sort of thing, this climbing up, which is a little bit unusual. But it's looking the same as the first lane, I will say. I'm sure I can just go across a couple more down here. Here's another one doing the same sort of thing. Okay, so I've not seen that directly before, but let's now open this card up and let's have another bit of a look around it and see if all the resistances look okay. And if they do, let's power it up and just see how far we can actually get with this. Lewis and Albero tell me they have been watching my videos and they have looked at these cards, but after a couple of weeks of looking around, they decided it wasn't quite for them. Or rather, no, that's not fair. They decided that it takes longer than a couple of weeks to learn this, and I totally agree. It took me, with a good grounding of electronics to start off, it probably took me about a year playing around before I was confident with GPU repair. And with motherboard, the same. Okay, this is another one. So some of the screws are already missing, doesn't surprise me. And we can take the board off and we can have a look. So first of all, there isn't really anything much in the way of thermal compound. Possibly they cleaned it off. So we can get rid of the heatsink. There seems to be some corrosion inside here on the heatsink, but this doesn't surprise me with Gran Canaria. I mean, Las Palmas, the capital, is by the sea. It's known, by the way, Las Palmas to be A, the capital city with the best climate in the world, and B, it's also known as Nomad City due to the number of tech startups there, people living there. You actually get, like, you know, all the infrastructure of a European country here with the prices of living in an African country, basically. So we have a very large cyber nomad community. If you're interested, search for cyber nomad Las Palmas, Las Palmas, you might say it, and you'll find it. Enough waffling. So this is our card. Let's see what we have in the way of resistances on this. So I'm on now normal resistance range, and we want to have a look. So 12 volts coming in. Well, there's no shorts on 12 volts. Now let's go to the 12 volts up here. One side of this connector is ground anyway. I'm pretty sure the 12 volts is coming in onto here, this current sense resistor. Oh, that looks like we have a short. Yes, we have a short on 12 volts. Do you see it on this current sense resistor here? So somewhere on here we have a shorted high side MOSFET. That's the first thing we have. That probably explains that increasing reading I was getting. So let's see if we can find out where that actually is. I'll just check the 3.3 volts as well, which is the fourth finger in. That's okay, no short there. So there's two rather large buck regulators here, which are probably going to be the ramp phase, as I'm not familiar with these cards at all. Yeah, like sort of 70 ohms, and that looks normal for a ramp phase. There's two here. That was reading 3.8k. Right, this one 12.5 is probably the PEX rail. That's the PCIe Express, or it's the voltage for the memory controller. But there's another one up here which might be memory controller. What was this one reading again? Well, that looks like RAM 69. This is almost certainly just a filter on the 12 volts input. We can check that. Just go find the other side of it. Here, yeah. We can check here. Yeah, we've seen the short here as well. So this is on the 12 volts coming in. Ah, something's broken here. Oh no, it's not. It's just a little rubber pad. It looks almost like a broken capacitor, but it's not. It's just like a little rubber pad to bounce the backing plate. Okay, that's all the supplies that I can see. Oh, there's one more here. I don't think I found this one before. What's this one reading? 7 kilo ohms. That looks okay. What's the V core reading? So that'll be these. Well, it's reading very low, but this is likely to read very low anyway. See, 0.2 with them shorted and 0.4 with them not shorted, so that doesn't surprise me. That's probably okay. So what we seem to have here is a short circuit on the 12 volts coming in from here through this current sense resistor, through this. Is this connected to it as well? Yeah, it's there as well. But this 12 volts doesn't have a short. So I'm fairly confident we can say that this is powering the memory controller, the PEX and the RAM, and this is probably powering the 4 coils here. So the short is probably going to be a high side MOSFET. This doesn't have individual MOSFETs, but it has these driver chips here. So let's zoom down on these. In fact, let's use the microscope and let's see what these actually are. You can see that we have a part number QA3111. So that's the part number, then some more numbers. I'm assuming the first part is actually the part number. And then here we have this chip. Yeah, UP9511P. So I'm fairly confident this is going to be the VRM controller, and these may be dual MOSFETs or they may be drivers. They're not single MOSFETs because there's one by each coil. So they're at least dual MOSFETs. So let's have a look to see if we can find the datasheet for these. I couldn't find a datasheet for the QA3111, but I can buy them. But I did find a datasheet for the UP9511, and that tells me all I need to know about these. So let's have a look at this datasheet. This is the datasheet for the UP9511. And you can see it's 1 to 8 phase synchronous rectified bucket controller. We have a pinout here, and if I just scroll this down a little bit, we can see a typical application. So it shows for each of the 1 to 8 channels, you have a pulse width modulation output and a current sense input, and then you have an external driver chip which drives MOSFETs, or quite possibly the MOSFETs are inside the driver chip, which is what we have, I'm sure. So we can see that each of these chips are actually drivers, and the MOSFETs are going to be inside them because they're not separate, and this is where we have a short. To work out which VRM, which voltage rail, has the short circuit high side MOSFET is actually quite simple. The way you do this is to have a look first at the resistance of the short to ground that you find on the 12 volts. So in this case it's 0.2 of an ohm. I'm on normal ohms range. Now we need to go to each of the coils that we can see and again measure resistance to ground. So we have one here, and what we're looking for is a resistance that reads the same as the one we found here, something the same as that 0.2. So we can see this one is 7.5 kilo ohms, 7.3 kilo ohms, 3.8k, that's high, 12.6 ohms or lower one, and we have two more here, 69, 69, and then we have these coils down here which we can get to on the bottom of the board. So that's these four, and that's the one. It's very close. It's actually reading 0.4, 0.4, 0.4. So that one is basically reading the same. I mean, there'll often be a slight difference with your meter. Is that one. Okay, so that's where the short is. It's on these coils here. Yeah, this phase down here, this is where your short circuit is. If we're lucky, we'll find that the VRM, which has the same resistance to ground as we're reading from here, is one with a single phase like this one. So there's just one coil and one driver. Here's another coil and the driver's probably over here. We know they're only on a single phase because the resistance reads different on the two of them. These two up here actually both read the same. So here we have two phases on one supply. This is almost certainly the supply to the memory, and you can see we have one driver here and we have one driver here. Resistance is 69 ohms, so we know the problem isn't here. The problem is here, and this has four phases, and this is where it gets more difficult in this case, or in this case, to actually find where the short circuit device is. This board in fact only has four phases down here, but it's common to have graphics cards and motherboards with 8 phases, 10, 12, 16 phases maybe on some very high powered ones. And when you get to these sort of boards with many phases, it is important that you can determine which high side MOSFET is the faulty one. One other thing I'll just mention, the resistance of these coils is extremely low, almost to zero. So in actual fact, it doesn't matter which side of the coil you measure to ground, you will get the same results regardless of which side you're actually reading from. So don't think you need to measure from one side of the coil or the other. They will both give you the same readings on a multimeter. Now let's have a close look at these circuits. I'll draw it out and I'll show you exactly where in the circuit the short actually is. This is not a short to ground. This is a short from the 12 volts coming in to the voltage rail that supplies whichever component, whether it's V-core, VRAM, PEX, memory controller supply. It's a short from 12 volts to there. It's not a short from that rail to ground. I've just moved to the other side of the screen because I have a nasty habit of drawing underneath the inset picture where you can't see it. Okay, so to stop that happening, I've just shifted over. This then is your 12 volt supply coming in. And from here, we have a number of VRMs. Each VRM is quite simple. So we have 2 MOSFETs in series connecting directly to ground. The 2 MOSFETs go to a controller. This is your VRM controller. I can't fit the whole word. VRM controller, okay. And the controller switches these MOSFETs on very rapidly, one after the other. Okay. From here, the junction between the two, we have a coil, and on the other side of the coil we have capacitors, usually lots of capacitors, not just one as I've shown, to ground. And then coming out of here is the supply to the load, whether it's the V-core, the VRAM or whichever. This circuit is called, many people call this a buck regulator, but it's actually a synchronous regulator. But they're sort of synonymous. This is a synchronous regulator. Call it whichever you wish, that's the correct term for it. So the way this circuit works, the 12 volts does not supply power to the load. When this MOSFET turns on, the 12 volts flows in here into the coil. But the coil has inductance and it will resist the flow of current. And what happens is, before the current can come out the other side, it has to charge the magnetic field inside the coil. So all the energy coming into here is being used, stored in the magnetic field that builds up. And once the magnetic field is saturated, that means it can no longer magnetize anymore, it's saturated, then the current will come through into the load. All the current. So at the point of saturation, the 12 volts will also appear here. And we don't want that to happen. This is loaders maybe running on for memory 1.35 volts. So this controller only switches the MOSFET on long enough to magnetize the coil. Before it's fully magnetized, saturated, it switches off again. So no more current is flowing in. It will not magnetize any further. What happens now is this one switches on and it effectively discharges the magnetism in the coil. And it's that magnetism collapsing is what generates the voltage to charge this capacitor and supply the load. And by controlling the amount of time this one is turned on in relation to the amount of time this one is turned on, you can control the amount of magnetism stored in the coil and you can control the voltage there. That is a simple VRM. Synchronous, not buck. Okay, so that is a normal single phase, but on ours we have some multi-phase. So we have a 2-phase supply, we have a 4-phase supply. I'll draw the 4-phase supply, but obviously from this you'll understand the 2-phase supply is basically the same thing. So here's the drawing, a bit of Dicky CAD, yeah, Dicky CAD. Copyright 2022, yeah. Okay, what we have here then are the 4 phases. This is the controller chip, and each of these is the high side MOSFET for each phase. And they're called high side because they connect to the 12 volts. And the other ones connected from the core to ground are low side, 4 of them. And the signals here would usually be called upper gate 0, because we start with 0 because we're computer minded, yeah. And lower gate 0, yeah. Upper gate 1, lower gate 1, and same for 2 and same for 3. Upper gate 2, lower gate 2, upper gate 3, lower gate 3, and so on, however many phases we have. And the way this works is just like the single VRM, but with added functionality, and that's it has multiple phases. So basically, in this case, the controller will switch the upper gate of this one on, so this draws power into here, magnetising the coil. And before it's fully magnetised, it switches that off and switches this on, and the magnetism collapses and goes down to V core, which is here. Yeah, this is your V core, your load. And these are where all the capacitors are. Lots and lots of capacitors from there to ground. Once that's happened, while this is still collapsing, it then switches on upper gate 1, powers this one on, and this charges this coil up with magnetism. And the same thing, switches off, switches on, and again that discharges into there. And that happens for all 4 phases. You can think of this a bit like either a 4-cylinder car, where each cylinder has got a different phase. It is a phase, so 90 degrees around the rotation, 360 degrees, each cylinder will fire in one order or another. So each cylinder fires one after another, and that's what gives the smooth rotation of the motor, and it all works fine, and it all can generate more power than just one cylinder could alone. Another way you can maybe think of this is a bit like a Gatling gun. You know those, especially them World War Ones, where you turn the handle and the barrel spun around and it fires a bullet out of each barrel in turn. And the reason for that is basically you can get a much higher fire rate. So it rotates the barrel for each bullet. That's each discharge of one of these. And by firing the bullet down the barrel, you generate heat friction, and this effectively generates electric friction with the resistance of the coil. So they get hot. Yeah, the MOSFETs get hot, the coils get hot, and it fires them in turn or in some sequence which it uses, so that each one is effectively handling a quarter of the load. It's only firing, if this thing was running 200,000 times a second, each one of these is only running at 50,000 times each. And it shares the load. So that's what this is doing. This business with the upper gate and the lower gate is called the drive to the MOSFETs. So here we have a pair of MOSFETs. High side, low side. Okay? And each one has to be fired in turn. This will be controlled by a pulse width modulator chip. PWM, and this basically sends out of it 4 sets of pulses. So phase 0, phase 1, let's call them PWM 0, PWM 1, PWM 2, PWM 3. So this is sending a pulse on each one in turn, yeah. Well, this pulse has to be converted into this. Switch this on, then switch this on, switch this on, and switch this on. So normally the pulse width modulator, the 4 of these go to the controller, which is off my piece of paper, so I can't show you exactly because it wasn't a very good. It was a dodgy CAD, yeah. That was a dodgy CAD drawing. But you can see that this is just effectively sending a pulse, and this chip is controlling the switching between the two for each time it's pulsed. Yeah. So you'll often find motherboards and graphics cards where you have a pulse width modulator, then you have a driver chip, one driver chip for each pair of MOSFETs. So 4 driver chips, 8 MOSFETs, one pulse width modulator. You'll find that, just to add on to this, I will just show you, normally there's another MOSFET here for each of the low side. So normally each low side MOSFET has 2 of them, and the gate of this one is connected to the gate of this one. So this switch is on alone to charge the magnetic field, and these 2 in parallel switch on together to discharge it. Normally this is one type of MOSFET, normally these 2 are a different type, but both the same. So now, in actual fact, what you'll normally find is one pulse width modulator, 4 drivers, one for each set of MOSFETs, and 3 MOSFETs in each phase. That's a very, very common topology that you'll find. To make things more integrated and smaller, everything's getting smaller these days, in more modern graphics cards and motherboards, you tend to find that you have the pulse width modulator with however many phases, and then the drivers are built in with the MOSFETs. So each of these pairs of MOSFETs is replaced by one chip. This is the chip. Inside the chip you have the 2 power MOSFETs connecting to ground, connecting to 12 volts. Inside here then you have some logic circuitry. This logic circuitry will have a power supply, often 5 volts or 3.3 volts, but it could be any supply that's on the board. It could be 12, but often it's 5 or 3.3, and the logic has coming into it PWM. So in the case of the first phase, PWM 0, and then we have another one of these driver chips, just the same thing, inside exactly the same as this one, and coming into here will be PWM 1 and 2 and 3. So you'll have your 4 of these chips. This effectively replaces the MOSFETs and the driver all in one chip, and these are basically called drivers, or VRM drivers. Coming out of this chip then will be a connection to the coil, going to the load. So this is what we are generally faced with when we try to diagnose the problems with these circuits. Now we know what the circuit looks like, I'll show you where the short is. So the short is in one of these MOSFETs. Say it was in this one. So what happens is this MOSFET internally goes short circuit from the drain to the source, and we've now got a connection from the 12 volts directly through the MOSFET to the coil. So when you power up, all the 12 volts comes down through here. In the first few microseconds it will magnetize the coil. As soon as the coil is now fully magnetized, this can't turn off, so the current now goes down here into these capacitors, into the load, and this will draw a massive current. If there's a fuse in the 12 volts, which there often is on higher end graphics cards, but not always, if there's a fuse, the fuse will blow. If there isn't a fuse and you've got a good power supply, ATX power supply, that's monitoring the current, then the ATX power supply will shut down. So you'll find your PC will switch on, for instance, and then switch back off again, and it often won't come back on unless you unplug the mains and do it again, which, by the way, is not a good idea if it's shut down the first time it did it for a reason. Every time you switch that ATX on, you'll send another burst of 12 volts down through here, more stress on the load, which is probably the GPU core or the CPU core. So that's the second thing. If you have a graphics card where they kind of cut corners and didn't fit fuses, and you have an ATX power supply that doesn't monitor the current very well, what will tend to happen then is this MOSFET here will set on fire, burning a hole in the PCB. Possibly the inductor will, well, actually the inductor won't melt, but tracks can burn out. All this current is going to cause damage. If you're really unlucky, the graphics card will set on fire. So that's what you need to watch for. And this is where your shorts are. So you now know the short is here into this coil. Short circuit high side MOSFET. This is why when we measure from the 12 volts, and I'll just refer back to the previous diagram, when you're measuring from the 12 volts, the resistance from here, here's your test meter. I always draw an analog meter. It could be a digital meter. When you measure to ground from the 12 volts, the resistance you see is the resistance of this load. Because if there's a short here, the current is flowing through the short. I mean, when I say current, your resistance meter injects a small voltage to measure the resistance. And it measures the resistance by working out how much current is flowing. So the test meter does send current into the circuit. The current flows through the short circuit MOSFET, through the coil, charges up these capacitors, and you see the resistance of the load. It's exactly the same thing as if you connected your test meter, and it would make sense if you connect one end to the coil, and you're connecting the other end to ground. Looking, I've drawn the meter backwards, But some guys, I know you'll actually use your digital multimeters backwards, red and black wires. So measuring here is the same as measuring here. This is why the resistance you see from the 12 volts to ground will match the resistance of whichever VRM has the shorted MOSFET. And with a single phase VRM, it's very simple to find that shorted MOSFET or driver. In the case of this, it's still the same. It's just that the MOSFETs are no longer separate components. They're inside this driver chip. The short is there. Okay. Capacitors. And the same thing applies when you measure from 12 volts. You will see the resistance of the load. And this is where the problem starts. Diagnosing faults in these circuits. Which MOSFET is short? And the reason it's a problem is this. You're measuring from the 12 volts to ground. The current's going down through one of these. Okay. If you then measure the resistance from here to ground, you'll actually measure the resistance of the load, as I've just explained to you. If you measure from here to ground, you'll measure the resistance to the load. If you measure from the top of this MOSFET, it's the same thing as measuring from the top of this MOSFET. It doesn't matter if your meter probe is put here, or it's put here, or it's put here, or it's put here. You are still measuring the same resistance. So you need a method to find out which of these high side MOSFETs is short. And that's what I'm going to show you in the next step of this video. I will just show you a few physical examples of what I've just explained on paper. So this graphics card has 6 phases here, 6 coils, and these have driver chips. So there's one square chip sitting next to the coil, and this is a driver chip. Okay. Above it, we have another. This is a single phase. And this has high side and low side MOSFETs. This actually has 2 high side and 2 low side, which is a little bit unusual. It's more common to find ones which have 1 high side and 2 low sides. In fact, I'll just show you that now. So here is another graphics card. This one's a 8800 GT, a bit older. And you can see with this one we have 2 coils. 2 phases, 1 high side MOSFET and 2 low side MOSFETs, 1 and 2. You can see that the 2 low side MOSFETs are the same type as each other, 4835N, and the single high side MOSFET is a different type, 4841N. This is very, very common. We can see another single phase here, and again 3 MOSFETs. The easiest way to find, which is the low side of the two that are the same, 4835Ns again, and this will be the 4841. Yeah, 4841. So that's very typical. And if we take a closer look at this one, this actually has, just to prove the rule of thumb I've just told you is not always correct, this has 4 MOSFETs, 4C10N. And if we look quickly, you'll see that the top 2 are connected in parallel. So these are one side of them, and this is the other side, drain and source. This is the source, and they're connected together. And then the source of these 2 will go to the drain of these 2. In fact, I'm sure you can see the large circuit trace that comes down here. Okay, and then the other 2 ends will connect to each other as well. So we have 2 pairs in parallel. Here's an example of a driver, VRM driver, IR3553M, 1 driver on each phase, and I'll just show you the data sheet, and you will see that each of these has 2 built-in MOSFETs. This is a typical application diagram for the IR3553, the one we were just looking at. There are many other drivers that you'll find on VRMs, on motherboards, graphics cards, but they all work basically the same as this one. So we have V in, this is your 12 volt supply, going to the high side MOSFET, which is integrated inside this chip. This then connects to the low side MOSFET, again integrated, and it connects to ground. From the junction of the 2, we have a connection to the coil, which is then driving the load V out. In our case, it was V core. And these are the capacitors which charge up on that rail to smooth the pulses and give a steady supply. You can see we have a signal here, PWM, pulse width modulation, coming in. This effectively controls the duty cycle of these 2 MOSFETs, therefore generating the required voltage through the coil. There's a few more signals, but these are basically to do with enable signals and current monitoring and such. There's nothing that we need to really worry about too much in this tutorial. We will also find on the board the pulse width modulator controller, which in this case is this IC. So this is sending pulses to each of the drivers in turn, and then the driver is controlling the on-off switching between the pair of MOSFETs on that synchronous regulator. And finally, this is the RTX 2060, the one which has a short circuit high side MOSFET. This again uses driver chips, part numbers QA3111, and I've not been able to find a datasheet for this particular chip, but I can find some information on the driver, the pulse width modulator, which is here. And this UP9511P just has 4 pulse width modulation outputs, which tells me that each of these contains the driver and the MOSFETs integrated. So our short circuit high side MOSFET is in one of these 4 driver chips, but which one? So let's have a look now at 10 different ways we can determine which is the faulty one, and let's see if each method actually works. Here is my Fluke multimeter. It's a very good multimeter. This will read resistance to 1/10 of an ohm. So if I short these 2 together, we can see we've got 0.2 ohms. Let's see if this meter can tell us which of these phases has a short circuit high side MOSFET. So I'll go from 12 volts coming in to each of the coils. That's reading 0.2. This one is reading 0.2. This one is reading 0.2, and this one is reading 0.2. So they all read exactly the same, and it doesn't matter which side of the coil I go to either, they all read exactly the same. So that multimeter is not going to tell me which of the coils has the short circuit high side MOSFET, which phase. But this multimeter can only read to 0.1 of an ohm. I have another multimeter which will read to 100th of an ohm, 0.01. So let's have a look to see if that can tell us which phase has a short circuit high side MOSFET. This is the Aneng AN8008, and this will read the resistance down to a 100th of an ohm. I'll just short the leads together and you can see it's reading 0.22, 0.21. Okay, 0.20 basically, with them shorted. So let's try this one. So we'll go from the 12 volts coming in here to each of these coils again, and let's see if we can determine which has the short circuit high side MOSFET. So that's reading 0.021, 1920. Basically the same as the leads shorted together. That's reading the same. That's reading the same. That's reading the same. So even with a multimeter that reads to a 100th of an ohm, we cannot determine which high side MOSFET is short circuit. So with the low ohms meter, I'm going to measure the resistance from 12 volts to each of these coils. The idea being that the driver which has the short circuit high side that's closest to the coil will give the lowest resistance. So this one's reading 0.027. That's on the 2 ohms range. Let me go to a more sensitive range. 28.7 micro ohms. What's this one reading? 29.8. Not much difference. What's this one reading? 30. What's this one reading? 301. So it seems that this first one, 28.3, is actually reading lower than all of the other ones. What? How much resistance are these? Oh yeah, the coils are reading very, very low, 0.029. It has very, very low resistance. But it looks like this one is the one that has the short to 12 volts, the one nearest the bottom of the card. To use the ESR meter, this relies on the fact that it's 100 kilohertz, which this uses. It will see the coil as a resistance. So let's have a look at what we have. So I'm going effectively, all this end of the coils are connected together. I'm going to the end of each one and see where the lowest resistance is. 0.14, 0.16. Did you see it? So I'm measuring across the coil, yeah, and when I come to the one with the short, I'll see the lowest. So 0.164, 0.15, 0.13, yeah, 0.12, 0.003. So that is also showing me that this is the one that has the short on it. So we have two methods, one using the short circuit finder, one using the ESR meter, that both point to this chip being the one that has the short circuit. But it's possible, although the multimeter cannot see the difference in the resistance here, it might be able to tell us which is the faulty one if we look at the drive signal coming into it from the controller. So let's have a look. So this is where the pulse width modulation drive comes in. I've tracked it from the chip. So that's reading 8.6k. That's reading 8.46k. 8.57k. And this one's reading 3.5 ohms. Method 3. Faulty chip. Okay? There's 3 ways to find it. About 1 month ago, I published a very, very popular video. And this video described how to convert a standard multimeter into a very, very sensitive short circuit finder. We tested the short circuit finder on the video and it worked very, very well. I then went on to publish a second video, a follow-up a week or two later, that dispelled some concerns that people had that this would damage circuitry that runs on low voltages such as GPU core, CPU core and so like. And we did some tests, proper tests on graphics cards, and proved that it wouldn't damage anything at all. So I've now reconstructed my short circuit finder. Let's see if this is actually sensitive enough to determine which of these four phases has the short circuit high side MOSFET. This is set to volts range, and you need a multimeter that is quite sensitive, so this reads down to 1/100th of a volt. We're now going to connect the positives to the 12 volts coming in. Then I'm going to try on each of these coils to see what reading I get. So this one is giving me 0.0001. This is giving me the same. This is giving me the same. So it's basically saying this is a dead short. Does this one read any different? No. So in this case, the short circuit finder is not going to tell us which one has the short. I was just about to give up on this method, but I've realised I may be able to increase the sensitivity of this further. So I'm going to go to the millivolts range on here, which is now showing overload. Because the voltage reading is so low, this may now help me. So I can now see 11.6 millivolts on this one. Next coil. 11.6, basically very similar. This one. 11.9, slightly higher. And much higher. Okay. Yeah, so this is definitely reading much lower on this one. Okay, we can see 7 millivolts. Yeah, 11 millivolts. Another very common method of short circuit finding that people use is voltage injection. So via this method, we inject a voltage into the short circuit to see what component gets hot. Now we know that all of the current is flowing through this MOSFET, the faulty one. We know it's this one. We've already determined that by well, a few methods now. But let's see whether this method is going to work. So in this case, we need to inject 12 volts into here, connect to ground. That's what we normally do, 12 volts to ground, and see what gets hot. I have my bench power supply. Now I need to set the voltage on this to be lower than the supply voltage for the GPU. That's the only way to be safe. It needs to be lower. And then I can set the current to flow whichever I wish. So I can now effectively short the two leads together. So we have the two leads, we short them together, and I can now dial up whatever current I want. So I can get into this maximum, just make sure the leads are sitting properly. I can get 5 amps. Okay, I can get 5 amps into the load. You would think that was probably plenty enough to warm something up. So let's connect this to our board and let's see what happens. Just to prove I have the polarity right, and I had the polarity right previously, I'll just connect an 8-way connector into the plug. That it fits this way, and you can see that the yellow is on the top. So this is your 12 volts, which goes to the inside end here, which is where I was measuring on the previous tests. So we know that's right. So I can connect the 12 volts to here, and the ground can go to ground somewhere on the board. So I'm just going to use I'll try the metal bracket first, see if I can actually get a good enough connection onto it. No, I don't get a good connection. They're only 1 point something amps. Let me find a better ground point than that one. With the leads shorted together, you can see I can get about 5 amps. But this isn't a dead short, it's about 0.2 of an ohm, which is the resistance of the GPU. So if I connect my power supply to here, I'm seeing about 0.8 of a volt. That's fine for this GPU. And I have about 1.6 amps, 1.7. Now, is the faulty part getting warm? And the answer is no, it isn't. I'll just leave it on a little bit. Let's get a little bit of time to see whether this actually gets warm. The GPU isn't particularly warm either. In fact, it's cold, really. Probably the reason it's wandering around slightly is probably a slightly bad connection on the end of the wire here. Okay. Any very slight difference in the resistance of the connection, or where I'm connecting to the ground or here, will obviously cause a slight fluctuation. Okay, it's been on a little while. No, it's not getting warm. Now you might suggest using an infrared camera. I don't have an infrared camera, but I do have a temperature meter, which I have a thermocouple, and I can certainly use this to see whether the short circuit device is any warmer than the next one. So this is the short circuit device, this one, and that's reading 27.6, 27.7. What's the other one reading? It actually reads warmer, 29.8, 29, it's reading the same, 28.9, 28.5, 28.4, okay, 28.2, and that's reading 28.1. The temperature's just dropping a little bit. That's probably because the thermocouple was in contact with something warmer. Does that one read just a little bit higher? 28.7, 28.2, 28.7. I want to see if I can actually get a definitive answer to this. Will it see the difference in the temperature? 28.5. I think we're going to have to say no. This is not generating enough heat to give any definitive answer. Sorry guys, but that method is a no. This is a slightly different variation on the method I just used. So in this case, we're injecting current again into the short from the 12 volts. And what we're going to do now is try to determine which of these coils the current is flowing through. The idea being that the one which has the short, which is passing current through the coil, will read a voltage across it. So we can go to the millivolts range on here, and we can actually have a look. So if there's no current flowing through the coil, and the coil has some resistance, albeit very low, we shouldn't see any voltage drop across it. So that one's reading 0. This one's reading 0. This one is reading 0. Does this one show a voltage drop? Yes, it does. So we know the current is flowing through this coil. So this method has determined which coil, which phase, has the short circuit high side MOSFET. This method is a little bit more esoteric, we could say. What I'm going to try now is see if I can find the short circuit phase by ring testing the coils. The idea of this is that the phase that has the short circuit on one end of the coil is going to V current. There's lots and lots of capacitors, and because we have a short circuit, the other end of the coil is going to the 12 volts, where there are also lots and lots of capacitors to ground off this rail. Now, if I effectively pulse the current through here, which I'm going to do very simply by just rapidly touching the crocodile clip against the 12 volts. If I do this and I put an oscilloscope on this end of the coil, I'm expecting that the one which has the short circuit, I'll just effectively just see the voltage going on and off, but on the other ones this end of the coil is effectively open circuit because both these MOSFETs are off. And I'm expecting to see like some sort of spike or pulse here, a ringing effect on the oscilloscope on all the good phases and not on the bad. I have no idea if this is going to work, but the theory seems good. So let's try it and let's see if we can determine which phase has a short circuit high side MOSFET by ring testing the coil. So with this method, I have my digital oscilloscope set up there. I'm going to put the scope probe on the coil. So we'll start with this one. And I'm now going to touch the power in instance to the 12 volts. So the power supply is set to 0.8 of a volt, maximum current, so it can't do any harm to anything. So I'm on the first one, coil. And let's just, I very briefly just touch the connection. Yeah, that's what I see on the oscilloscope. You see, I see like a pulse with like a lot of ziggly-zaggly stuff at the top of it. That's a technical term, by the way, ziggly-zaggly stuff. Let's just turn up one more sensitivity. That one probably went off the screen. Yeah, big pulse with ziggly-zaggly stuff on the top. And what I'm interested to know is the one with the short behaving differently? I'll just move it down a little bit so we can actually get on the screen a bit better. There we go. Yeah, let's go to the next one. Pulsing with ziggly-zaggly stuff. Does this one look any different? And I'd have to say, no, it doesn't. So this interesting method doesn't actually appear to help. Okay, so that one was a failure. Here's another idea which is more fun than use, but you know, let's have some fun. So I have here just an inductor coil connected to a scope probe, and you'll see my oscilloscope there on the screen. So I'm going to hold this coil close to the other one and touching it and see when that magnetizes the coil, because the current's flowing through this one. This has a short. Do I see anything induced into this one? So we'll just touch against the 12 volts. I have my scope on the most sensitive settings, and this doesn't work. Okay, this doesn't do anything. I do know that these casings on these are designed to keep the magnetic field inside, so I'm not totally surprised. Just for that reason it doesn't work. But let's sort of go underneath, because just on the side of the board it's there, and we might see something from this side, although I doubt it. Let's just try it. No, again, I'm just touching it, but nothing's happening. So that method, although it was interesting, didn't do anything. Maybe with a sensitive enough pickup, but this doesn't work. Many people ask in the comments to my videos on short circuit finding, if I remove the coils one at a time until the short goes away, will that tell me which MOSFET is short? And the answer to that is yes, clearly that will, because we can see on the diagram, the explanation, that the short is feeding current through a coil, one of them. And if you remove that coil and break the circuit, then yes, that will tell you which high side MOSFET is short. However, if you've never tried, or if you have tried to remove these coils, this is not easy to do. I have tried, and it's very difficult to get off. I've taken them off for salvage purposes in the past, but these are not easy to desolder. They really aren't. There's a lot of heavy planes in here. I think the best answer to the question, can I remove the coils, is if you've got the equipment good enough to remove these, so we're talking a preheater, a good preheater, strong hot air, something like a quick 861DW. If you've got that sort of kit to do that, then you have no excuse not to own the other kit that will do it a lot easier for you. Okay? I think that's enough said about that one. And in a similar vein, can I remove the MOSFETs until the short goes away? Yes, you can. But as pointed out with removing the coils, they're not that easy to remove. a lot of these drivers, which are not MOSFETs, will have connections underneath, and they're not that easy to replace either. So once again, if you've got the equipment good enough to remove these, which is going to be a preheater, it's something cheap like the little Carder 853B plus hot air, yes, you can do it, but come on guys, I've just shown you there's much easier ways to do it than that. Having said that, now we know this is the short circuit device, we're going to have to remove this because it needs replacing. So I'll show you now how I actually go about removing one of these. The first trick about removing these is to use the preheater, which I'm going to use. So we need to get a lot of heat in from under the board, such that when we come to use the hot air on the top, we don't need to heat it up so much. Bear in mind there's a lot of capacitors around here, and if you get too much heat into these, they'll bulge, in which case they'll fail, or they'll go bang and make a mess, and they don't smell very nice. So the first thing I'm going to do is just cover over these with a little bit of Kapton tape. Aluminium foil is also quite good for this. So I'm going to try at least to protect them from the heat. I'm also going to come in with the heat from this direction as best I can. So I'm trying to keep the heat away from these a little bit. Having said that, I may still end up having to remove at least these ones at the end. The second point, as I just made then, is to use a preheater. So this is mine, you've seen this before, little Carder 853B. And this is a hot air preheater. You can see it just pushes hot air from underneath the PCB. So I'll get the board onto this and then we'll get this thing removed. I often desolder components by adding some leaded solder to the pins first to work with the melting point. But in the case of these, there are pads underneath the device, so that really isn't going to help you. What I would still suggest you do is add a little bit of flux. So we get a little bit of flux around here. Now these have by the driver some small surface mount components. Normally I would take a photograph before working so that I can refer back to that afterwards. If I've knocked something off the board or dislodged something, I can see where it goes. But with these, because they're all the same and it repeats the same circuit, the components next to each one is the same as the components next to the other one. So if I do dislodge something, in this case I can easily work out what it was. Now let's switch on the preheater. So it's on and it's on heat. I've turned the dial up. There's no temperature setting such on this, it's just as a dial which goes from cold to hot. So there's a little bit of guesswork. But I'm going to warm this up. I'm not going to use a thermocouple because I'm used to working with this equipment, but a thermocouple is a good idea if you're not. And you want to try and get it up to about 120 degrees or something similar to that. That's been on for a couple of minutes, so it's warming up quite nicely now. I'm now going to turn the preheater up to full. I'm going to try to do this right-handed, which is a bit awkward because the brackets here and I might actually burn the back of my wrist. Yeah, I can get it from this direction. Let's get the hot air. So hot air on 450 degrees maximum airflow using the quick 861DW, and I'm now going to try and remove this. Oh. Well, that's taken a lot of heat and it's actually overheating the capacitors, and I still can't desolder it. I actually got this unsoldered before that will give up. So I'm going to have to cool this down again, put it onto low and remove these capacitors before I'll come back in and have another go to change this. As you can see, and as I suspected, these capacitors just bulged. The bad smell came from that. That was the first thing I noticed, was a bad smell, and I thought these are going to go bang in a minute. You can probably see on that one, the bottom of it's all bulged outwards. So I've now removed all three capacitors. This one's not quite so bad. And we can try again. And you can see how much heat it's taking to get into this. See, that one's gone, the base of it's bulged outwards. So this should answer your question, well, can I just remove the coils or the MOSFETs until the short goes away? And the answer is yes, but do you really want to? Okay, so we'll get over here again and let's have another go at removing this driver chip. Those were the 10 different methods I could think of to locate a short circuit high side MOSFET in a multi-phase VRM. I'll just go through them briefly, a little resume, and then we can all have our thoughts in the comments below. Very interested to know what you guys would think about that, and also any favourite methods I use and anything else you can think of that I didn't think of. So method number one, measuring the resistance from each coil to 12 volts with a multimeter, doesn't work. Method number two, measuring from each coil to 12 volts with a milliometer, it worked. Method number three, using the ESR meter, I think was a dramatic success, and I think actually some of you guys might have been quite surprised by how well that method works. Method four, measuring the resistance from the gate to ground. If the MOSFETs, yeah, this will work pretty much every time, but it does depend on the internal damage to the short circuit MOSFET. In the case of drivers like these, it works dramatically well on this board, but I wouldn't guarantee it would work on every board. It depends on what's happened inside the driver chip. Method 5, using the $1 short circuit finder. I think that was quite an impressive success again, considering how cheap that thing was to build. And I will link the video again at the end credits of this one. You'll see a link to that video. Voltage injection to see what gets hot. I know a lot of you are very strong proponents of this one, but it didn't work. Nothing got hot. Not even using a thermocouple, which could measure the 0.1 of a degree, could I say that that one driver, which had the short, was getting any hotter than the other ones. Voltage injection with a millivolt meter to measure the voltage drop across each coil. I think that was very, very impressive, the results we saw on that one, and I hope you guys would like to agree with that. The more esoteric ones, pulsing the voltage and seeing if we can make the coil ring on the ones that open circuit at one end, basically. It didn't do anything. Same with using effectively an inductance coil and an oscilloscope to see if we could induce some current from the one that had the short. So you're passing current through that coil, you can induce into another and see some voltage. Possibly would work, but certainly not with the equipment I was using. Remove the coils. That ain't easy, guys. I mean, you've just seen the end of that video. I could get the coils to desolder. Removing the MOSFETs. Well, I mean, that was even more difficult. In the case of this board, I need to get that MOSFET off because it's short, and yet it appears to have welded itself to the board. Even the inductor that was close to it was desoldering it. So removing the MOSFETs, yeah, but come on, guys, there's got to be much easier ways to do it than that. In fact, I've shown you much easier ways to do it than that. Yeah. Okay, so to end that one, I hope you enjoyed that, and I sincerely hope that my first comments, that no matter whether you're a beginner, whether you're intermediate, or whether you are experienced at this sort of work, I am sure you've learned something today. I'll see you all very soon on the next Learn Electronics Repair video. Ciao for now, guys.